All right, let's just jump right in. Welcome to today's Explainer, where we are tackling a massive headache in modern AI. We're talking about getting large language models to actually efficiently route queries. Today, we're unpacking a breakthrough framework called ReCal, which stands for Reward Calibration. Now, if you work with AI agents, multi-model setups, or reinforcement learning, you already know that dynamically picking the right model based on query complexity is essentially the holy grail. It promises massive efficiency. But, as we're going to see, the current reinforcement learning methods we use to optimize these routing policies are just fundamentally flawed. So today, we're going to break down exactly how ReCal steps in and fixes the whole thing.
So we really have to start with the multi-million-dollar question here. Why does RL-based LLM routing consistently break down? It's wild because when developers apply interaction feedback to optimize routers, everything seems totally fine at first. But the second you apply it to heterogeneous task distributions, a wide, messy variety of tasks with totally different difficulty levels, the whole system just falls apart. And what's really fascinating from the research is that this isn't just some minor bug we can patch over. It's an actual structural failure in how the AI learns from its rewards. Here is our roadmap for today. 1. The LLM routing problem. 2. Introducing the ReCal framework. 3. Unpacking ReCal's 2 layers. 4. The impact on AI architectures. And 5. Actionable next steps for developers. Starting with part 1, the LLM routing problem, and what we call the scalar trap. Think about the crazy balancing act these traditional routers face every single day. You want the answer to be correct, you want it formatted perfectly, and you absolutely need it to be fast. But legacy systems just mash all these conflicting goals together into one single scalar reward. It's kind of like grading a student with one single score that combines their math accuracy, their handwriting, and how fast they finish the test. If the router gets a sudden spike in its reward, the system literally has no idea if the AI used incredible reasoning or if it just got lucky and nailed the formatting. The optimization signals are totally conflicted. And man, that creates a dangerous domino effect. Because those signals are all shoved into a blender, you end up with massive reward variance across different instances. Some samples spit out wild, highly variable rewards, which immediately introduces optimization bias. The router effectively just takes the path of least resistance. It steers straight toward trivially easy samples and completely ignores the genuinely informative ones. The direct result? Your training curves get incredibly noisy, policy entropy collapses way too early, and ultimately, your routing accuracy just hits a wall way below its theoretical limit. Which brings us to part 2, introducing the ReCal framework, or reward calibration. This is a total paradigm shift. Think about monolithic reward aggregation, that old, noisy, legacy method of summing up correctness, format, and latency penalties into one ambiguous number. ReCal totally ditches that. Instead, it uses hierarchical reward decomposition. It replaces that monolithic mess with a super clean, structured signal pipeline that actually targets the root causes of unstable training in these multi-model setups. So how exactly does it pull this off? Let's dive into part 3, unpacking ReCal's 2 layers, decomposition and optimization. Layer 1 is that hierarchical reward decomposition. Basically, instead of squashing everything together, it isolates every single objective, correctness, format compliance, latency constraints, into discrete separate components, and then it calculates the advantage estimates for each of those components individually. This is huge, guys, because isolating them prevents something silly like basic format compliance from masking a total failure in reasoning correctness. It allows the policy gradient to actually update routing weights independently for every single goal. Once those signals are isolated, we hit layer 2, distribution-aware optimization. This is where it calibrates the variability of the optimization itself. It pulls this off using 2 key tricks: variance-aware reweighting and per-dataset normalization. This basically ensures that wildly different difficulty scales and reward magnitudes across messy tasks don't just hijack the entire optimization landscape. It means tasks that naturally have super high reward ceilings can't bully or overshadow the tasks with tighter, stricter constraints anymore. Zooming in on that variance-aware reweighting for a second, if a sample is literally just trivially easy, or on the flip side, way too chaotic and high variance, ReCal essentially just turns down the volume on those gradients. But it keeps the signal strong on the samples that actually teach the model something useful. The result is this beautifully calibrated optimization surface. Your routing policy finally gets consistent, apples-to-apples learning signals, no matter how hard the task is. It's finally learning based on actual query complexity, not just riding a wave of reward noise. Moving on to part 4, the actual impact on AI architectures. We're talking smoother curves and much cheaper inference.
The proof is absolutely in the data here. Across 7 completely distinct datasets, ReCal showed consistent, undeniable improvements in both routing performance and training stability when stacked up against standard RL baselines. Because it automates the signal isolation, multi-objective routing finally works right out of the box without engineers having to sit there relying on completely heuristic weight balancing. Predictable convergence is actually achievable now. And for production systems, this is a total game changer. Because ReCal stabilizes the training loop so well, you can confidently shove those simple queries over to your cheaper open models. That lets you reserve your incredibly expensive closed models strictly for the heavy lifting and complex reasoning. Plus, thanks to that variance calibration, you dramatically cut down on the need for endless hyperparameter sweeping. You get smoother reward curves, way fewer policy collapse events, and you can reliably balance cost and quality even when your traffic patterns are all over the place. Now, if you're suddenly panicking about having to rip out your entire existing stack to use this, don't. Crucially, ReCal does not mess with your base models at all. It operates strictly at the reward calculation and gradient normalization layers, so it is 100% compatible with whatever router implementations you're already using that rely on interaction feedback. All right, part 5, next steps for developers. Let's look at the playbook. So here is the exact pipeline you need to implement. First, go audit your reward function right now to see if you're relying on single scalar rewards. Second, migrate that over to a multi-component structure where every objective gets its own advantage estimate. Third, integrate those component-wise advantages into your policy gradient updates and make sure to calculate them before you aggregate anything. Fourth, normalize your rewards per dataset or task cluster so the trivial stuff doesn't take over. And finally, test this brand new pipeline against your baseline on a held-out, messy dataset. While you're running that test, you've got to watch your metrics like a hawk. Specifically, monitor your policy entropy and your reward variance incredibly closely during those first 1,000 steps to make sure the calibration is actually doing its job. Here's a great pro tip straight from the researchers. If you notice your entropy dropping way too fast, your variance reweighting might be a bit too aggressive. On the flip side, if your reward curves still look like a noisy mess, your per dataset normalization is probably misaligned. The good news is you absolutely do not have to build this from scratch. The team put together a reference implementation, and you can grab it at anonymous.foropen.science/r/ReCal. Just clone the repo, map your current reward functions over to their hierarchical setup, and run a controlled ablation against what you currently have in production. Just do yourself a favor and validate the calibration against your own latency and cost rules before you point live traffic at it. We're going to leave you with this thought straight from the research. If you are running an RL-based router, audit your reward function immediately. Single scalar rewards will lead to the same credit assignment and variance issues that ReCal solves. The days of throwing every single metric into a blender and just crossing our fingers that the AI figures it out are totally over. Hierarchical decomposition is the path forward here. The real question is, how much optimization are you currently losing to this scalar trap? Thanks so much for joining us for this explainer, and we will catch you next time.